So we've seen how Venn diagrams can help us generate some probabilities. Now let's take a look at how generating a table, and sometimes being given a table of values, can help us generate some probabilities as well. And we'll stick with the examples that we're already familiar with. So over to the left-hand side, you'll see that we have the Venn diagram for the blood breath test. Please stop. And we want to take and break this down and put it into the table to the right. So I do apologize on the video here. For some reason, this line has shown up in the middle. It's really supposed to just be shifted over here, so don't pay any attention to that at this point. But what I want to do is I want to take the values from the Venn diagram and put them into this table, which is a two-way table that we saw earlier in the year, where we have breath as our variable and blood as our variable. Those are the two tests that we have. And the Y and N will simply stand for yes and no. Did you get that particular test or did you not? And then we'll have a total column. So I'm going to fill in the first line, and the first line I'm going to do is for those people that had both a breath and a blood test, so yes and yes, and that's our intersection of 0.22. The next cell over is those people who had a blood but didn't have a breath, and that would be 0.14 for a total of 0.36. So the 36 total that had the breath test, sorry, had the blood test, and then how they varied within the breath test segment. The next one down, so those people that had a breath but did not have a blood test would be 0.56. Those people who had neither of the tests, no and no, would be this piece on the outside, the 0.08, for a total of 0.64. And the two-way table should always generate totals for the table that equal 1, so you'll realize that the 0.36 and the 0.64 over here in the right-hand column do equal 100% of the values. And then if I look at breath test yes, this is my 0.78. And if I look at breath test no, this is my 0.22. And together, the 0.78 and the 0.22 also equal 1 together. So take a second, just make sure that those numbers make sense to you and you understand exactly where I got them from. The question that we're trying to answer here is the first one: are giving a suspect a blood test and a breath test mutually exclusive? So we keep coming back to this question. And again, mutually exclusive, meaning are they disjoint? And from the Venn diagram, it's fairly obvious. But from the table, if we were only looking at the table, would we be able to determine whether or not these two events, blood test and breath test, whether or not they are disjoint? And we can determine that by looking at this cell right here, the yes and yes cell, the intersection of breath and blood. And since the intersection of breath and blood has a positive value in it, has a non-zero value in it, we know that they are not disjoint, they are not mutually exclusive. So the answer to this would be no, since P of A intersect B is greater than 0, they are not disjoint. And again, don't get that confused with independent, because that's the second question. Are giving the two tests independent of each other? I would like you to take a second, because I know that the last video has really addressed this topic. So take a second and see if you can determine with the given information from this particular table or the Venn diagram, doesn't matter to me how you do it, can you determine whether or not giving the two tests are independent of each other? So go ahead and pause it. Look back in your notes if you need to determine what formulaic way, what algebraic way you could go about to determine whether or not two things are independent. I'm guessing you came across this formula, the P of B given A equaling P of B formula for independence. And again, there's a little question mark above there because I'm trying to see whether or not they are independent. I'm not going to assume they are. So I'm going to do some calculations based off of my table of values and plug them in and see whether or not I get an equivalent statement for P of B given A and P of B. So let's start with P of B given A. So P of B given A we know is P of A intersect B all over P of A. And P of A intersect B is the intersection of the blood and breath test, which is the 0.22, divided by P of A. So P of A is the entire circle on the left-hand side, that big blue circle in your notes, or at least on my screen here. So that's the 0.78. And that's the probability that you got a breath test. That's where the 0.78 is coming from. So 0.22 divided by 0.78 is approximately 0.282. You can do that on your calculator. That value needs to be equal to P of B, getting a blood test. And P of B, we can see, comes from the top row of the table. P of B is equal to 0.36. And it's fairly obvious to me that 0.36 and 0.282 are not very close to being the same values. So not only are they not disjoint, these events are also not independent. Okay. We're going to move on to the next slide where we're going to kind of build on this. I'm sorry, I had to do it. I mean, when you're sitting around your house all day by yourself making math videos, every once in a while you just got to have some fun, so hope you appreciate the old Rickroll. So moving on to example number 8, though, back to the book where we have displays and equations and displays. I'm going to ask you to go ahead and make the table for the variables displays and equations. And just to make sure that we're all on the same page with this, let me help you at least set it up. And there's a couple of missing lines here, so I'm going to draw a vertical line here. You should draw one. Let's draw a horizontal line here. I feel like Bob Ross, the painter dude. Let's just put a little horizontal line here. Why don't we do, the top will be the equation variable, and then on the left-hand side, this will be our display variable. Yeah, that says display. And we'll just go with yes, no, total again, yes, no, total. And you have the Venn diagram, but you also have the values here in the example. So take a second and, number one, fill in the table with all the values. And then for B, C, and D, go ahead and try to answer those questions based off of the information that the table provides you. All right, take a second to do this. Pause it, go ahead and do it, and then start it up when you're done again. So maybe before going on to B, C, and D, take a look at the numbers that I have from my table and make sure that we match, that we are totaling again 100% of the values on the marginals, the 0.48 and 0.52, as well as the 0.27 and 0.73, and make sure that your conditionals are broken down the same way as mine. If you need a little help getting started on B, just making sure you understand what the question's asking, they're asking you what the probability that a randomly selected page with an equation also had a data display. So we're talking about the probability of having a data display given we know we had an equation for B. For C, you're asking whether or not they're disjoint. So this should be a question about looking at data intersect equations. And then for the last one, taking your answer from part B, checking that the probability of data given equation is equal to the probability of data. So go ahead and generate some values for B, C, and D, and then check back and make sure you have the right answers. Okay, and hopefully this is what you came up with. For the conditional in part B, probability of display given equation would be display and equation, which is 0.07 from right here in the table, divided by the probability of an equation, and the probability of the equation was just 0.27. So 0.07 divided by 0.27 gives you a 0.2593. Question C asks whether or not these are disjoint, and again, disjoint would mean that they have no intersection. We just saw in the numerator of the last one that 0.07 is the intersection, so 0.07 is not equal to 0, so these are not disjoint. And then finally, whether or not they are independent. So we might as well use one of the values we already have, the probability of data given equation, which is 0.2593, and whether or not that equals, I'm sorry, not data, display. The probability of display given equation, whether or not that equals probability of display. And the probability of display is over here at 0.48. And we see that those two values, 0.2593 and 0.48, are not equal to each other. So these are not independent. That knowing that there is a data display or an equation on a page changes the likelihood of the other type of display being on the page as well. Okay, so the final type of display that we're going to use to help us out with probabilities are referred to as tree diagrams, and we touched upon these a little bit at the beginning of our unit where we talked about flipping coins and generating the number of female and male dogs. We thought of this branching out of each successive event being a new branch on a tree. So go ahead and read this little blurb here about Maryland highway safety, and then we're going to talk about how to generate a tree diagram and answer some questions. Okay, so to generate a tree diagram for this, I want to start with the event that I'm talking about. And the event that needs to occur is there needs to be an accident. So I'm going to start over here and say, okay, let's say that we have an accident. If we have an accident, there are two things that could have happened from this accident. We know that, and so when I say that there are two things, I'm going to have two outcomes coming off of the accident. The accident could have occurred with a driver wearing a seatbelt or no seatbelt. So SB and NB meaning seatbelt, no belt. And the percentages that are associated were 77, so a probability of 0.77 and then a probability of 0.23. So off of each branch, I'm going to have what the event is, that you wore the seatbelt or you didn't, and then the corresponding probability. Off of each of these, there are two things that come out of the accident. So out of the 77%, you could have been okay after the accident, or you could have been injured after the accident. So there are two outcomes there as well. There could be many more than two outcomes, but for the ones that we're going to be dealing with, generally we're going to have only a couple of different outcomes. From the wording in this problem, we know that 92% of those who wore the seatbelt were okay, meaning that 8% got injured. And for those who didn't wear the seatbelt, again, the outcomes were either you were okay or you were injured. For those that were okay, 63% were okay when they didn't wear the seatbelt, where 37% were not okay. We can travel the path of our tree diagram to generate all of the probabilities for each outcome for wearing and not wearing the seatbelt. And what I mean by that is, if there was an accident, there's 4 different outcomes. There's the outcome of seatbelt and okay. There's the outcome of seatbelt and injured. No seatbelt, injured. No seatbelt, okay. And each of these would be generally an and statement in between. You wore your seatbelt and you came out okay. You didn't wear your seatbelt and you came out injured. So if I want to generate the probabilities for each of these branches, so the event of seatbelt and okay. So that would be, oops, let me get my pen back. That would be seatbelt and okay. Should just be the product of 0.77 and 0.92. So 0.77 times 0.92 is 0.708. So the likelihood of you of being in the accident with the seatbelt on and ending up okay, 0.708. For this one, this would be the probability of seatbelt and injured, and that would just be the product of 0.77 and 0.08, which would be 0.062. For here, we would have no seatbelt and okay. and the probability of you not wearing your seatbelt and being okay, 0.145, and then no seatbelt and injured is going to be a little higher than that, is going to be actually a little smaller, 0.085. If you were to take all four of these and add them up, the 708, 062, 145, and 085, they should add up to 1. These are all of the possible outcomes for you being in an accident. Okay, so this is how we're going to use tree diagrams to help us answer some questions. We're going to go on to the next video now to answer the following questions in the packet because my time is up on this one.